Hello, everyone. It's my honor to be here to present my work based on the HIsarna microfacility to simulate the based on the FactSage microfacility to simulate the HIsarna process. I'm ZhimingYan, a research fellow from WMG, the University of Warwick, and also this work support from Professor Zhu and the PhD student. And also we are great thanks for the data from Technology Center provided by Hans and Quinn. So today I will give you a presentation including the 5 parts. The first part is the introduction. So as we all know, the iron making and the steel making industry is the big sector for the CO2 emission. So the internal CO2 steel program was established to develop technologies to reduce CO2 emission. And there are 4 selected processes. And one is the CCS or CCUS for the top gas from blast furnace recycling. And the second one is HIsarna melting reduction process. The third one is the gas-based reduction. So we use the hydrogen to replace the fossil fuel. And the first one is electrolytes of the iron ore. So this is the HIsarna furnace. So it's divided 2 parts. We have a cyclone CCF in the top, and it's mainly for iron ore and oxygen feed, and the pre-melted and the pre-reduction. And also the off gas go out from the top. And the bottom part is the smelting reduction vessel, SRV. So we have the coke injection here, and the slag contain the melting iron oxide will be reduced here and produce hot metal, and the hot metal tapped from the bottom and the slag tapped from here. And here is another combustion lens with pure oxygen to preheat to produce the heat required for the reduction, the melting, or for all the heat required from the needed for the furnace. And then the FactSage is a powerful tool for modeling with thermodynamic equilibrium modeling calculations, and especially in the iron making and steel making process is very useful. So in this work, the process involved slag, metal, gas, refractory. They have a liquid, solid, and the gas phases. And then the reaction involved reduction, gasification, combustion, and also the slag metal reduction. And also we should consider about this sulfurization, dephosphorylation, and the deoxygen. So then it's a very complicated process. So fortunately, we have the EERZ model. So the EERZ model is effective equilibrium reaction zone model. In the EERZ model, a complex process is divided into finite number of reaction zones in which all phases within the effective reaction zone located near the interface we'll consider about is reached equilibrium. So we can use the FactSage, even though it's a thermodynamic model, then we can combine with the EERZ model to simulate the kinetics. So then the second part is the modeling description. So here is the HIsarna furnace. So we divide this process into 12 reaction zones. So the reaction zone 1 is the combustion in the CCF. So we have oxygen in here, and the off gas from the SRV contain the CO, and the hydrogen will be fully combusted here. And the reaction zone 2 is the melting and the pre-reduction. So the iron ore injection from here and will be melted by the heat produced zone 1, and also reduced, partially reduced by the CO or hydrogen here. And then the off gas from zone 1 and the zone 2 will be homogenized in the reaction zone 3 and then go out of the furnace. So in the SRV, we have the melting ore dropped here, and we also have the off-gas ups. So we have a melting ore reduction here, and then the melting ore will be mixture here with the slag in the SRV. So we have zone 4 for the mixture of melting ore. And the zone reaction 6 is the coal injection. So we are considering of the coal pyrolysis and the gasification here. And the zone 7, reaction 7 is the slag reduction by the coke, by the gas produced from reaction zone 6. And then the metal produced will go to here. And here, reaction 8, we also consider about a slag reaction with the hot metal. And then the reaction 9 is the combustion. Oxygen injection here, and the off-gas produced, even a little bit carbon particles will be oxidized here and the combustion here and produce the heat required for the whole furnace. And then the 10, 11, 12 will consider about the off-gas in SRV homogenized, the slag in SRV homogenized, and the hot metal homogenized. And during the whole process, we'll also consider about all the insufficient heat change, the energy needed can be recorded by FactSage, and at the end we can calculate the heat loss and also the total heat loss. And so here is the flow chart for the whole calculation. So we have start and we read the materials and we do the calculation. So we do the reaction one by one from the CCF to SRV, then for the homogenized, and then we save the result. And when the time is not reach our target time, then we do this loop again and again until we finish our calculation. Then the third part is the model validation. So first, the table 1 shows the input and output of the model calculation. So this is the date we used for the model simulation. So we have iron ore injection, the flux injection, the coke injection, and the air as the carrier gas for the iron ore, the nitrogen as the carrier gas for the coke, and the oxygen combustion needed for the CCF and SRV. So we also have the output, hot metal, slag, off-gas in SRV and the CCF, and also the dust. So the amount of hot metal produced is around 7 tons per hour. It's based on the plant date, and according to this, we use the coke consumption is about 760 kilo per ton, and the slag generated is less than 300 kilogram per ton of hot metal. All this state is in a good agreement with the pilot plant trial state. And here is the composition of the input materials, mainly from the iron ore and lime, and also the coke. So this figure shows the slag composition and the hot metal composition from the comparison between the industry date and the calculation date. So it looks like the slag composition agree with each other very well, and also the hot metal composition, the carbon content a little bit higher in the plant date, but in the plant date, the phosphorus is a little bit lower than the calculation. So theoretically, this process, the slag, we can say the slag contain about 6 or 7% of FeO. That means the oxygen potential is higher than the blast furnace operation. Then it's good for dephosphorylation. But for our calculation, there may be the coefficient or the kinetics parameter setting. If we match the other element for this element, it's not good enough, but we can do it development or improvement in the future. And here is the slack composition from the HIsarna. So here is the red point is from the industry date. So we can see that the basicity is around 1.2. And if we increase the basicity a little bit, the melting temperature will be increased very rapidly. But if you decrease the basicity, the viscosity, the desulfurization will be decreased. If we increase the FeO content in the slag, the melting temperature will be decreased as well as the viscosity, but the metal yield or the productivity will be decreased. These two figures shows the off gas of the SRV and the CCF, and the date looks in a good agreement with the plant date. And the PCR we define like this. We use CO2 plus H2O, divide all the CO, CO2, hydrogen, and the moisture. That means the high value means the high efficiency of this kind of gas. So the PCR measured is more than 95 in the CCF. That means we have a high energy efficiency in this process. And then after developed this model, we use this model to simulate the titanium magnetite ore injection. So this is the composition of the titanium magnetite. So we can see that we have 7% of titanium in the iron ore and around 30% FeO. This is the main effect, the difference, the FeO content and the titanium content. So after the calculation, we can see that the input and output difference, since we have no iron content in the titanium magnetite ore, so we need more iron ore injection here. But since we have high FeO content, that means we need less coal for the reduction of Fe2O3. So that means the coal consumption has a little bit decrease. Correspondingly, the off gas has a little bit decrease as well. But the slag volume increase since the breed of this kind of titanium magnet ore is not as good as the previous iron ore. So this is the element in the slag, or the component in the slag, or the element in the hot metal change with the injection time. So this point is the injection point. So when the injection point happens, the basicity decreased from 1.2 to 1.1, and the titanium content in the slag is to about close to 25%. And the magnetite and the alumina has a little bit increase since the titanium magnetite ore has high content of MgO and alumina. And the other element also has changed accordingly based on the composition from the iron ore and also the off gas. So this is the slag with titanium containing. So the red point is from the calculation. The basicity is 1.1. That's the reason we decrease the basicity, because if we increase a little bit higher, the slag liquid temperature would increase rapidly. So even the temperature is the basicity is 1.1, the liquid is around 1475. That's still a little bit higher than the current operation temperature. But the viscosity calculated and the density calculated, they are good for operation. In the blast furnace operation, the titanium ore will have some serious issues such as the slag forming because of the high viscosity and also has no sulfide capacity. But in this process, since the oxygen potential is higher than the blast furnace, the titanium oxides will not be reduced that much and will be forbidden that kind of phenomena. So that means the titanium, this furnace can be a good tool to melting this kind of hard use materials, but we still need more investigation because this is only simulation. We need more experiment investigation to check out the slag properties or something else. Here is the energy distribution. So the most significant heat consumption is followed by the off-gas sensible. But this kind of heat can be recovered in the future, and also the heat load decreased since we decreased the coal injection. And meanwhile, the energy needed for reaction decreased because we have a high FU content in the magnetite ore. The increased slag volume, the slag sensible is increased because we have the slag volume has been increased. Okay, so here is the brief summary, and we use the FactSage combined with the HIsarna model to build a HIsarna process simulation model. And this model also has been used to investigate the titanium magnet ore injection in this process. And here is the main conclusions. I will not repeat. Thanks all. Here is my presentation today. And if this work has been published, so if anyone interested and want to get more details, is welcome to have a look and welcome any comments. Thanks.